Alright, so in just a matter of seconds, I converted my fundamental circle constant program to find E. Honestly, most of the effort, most of the time taken was just making sure that I cleaned out all of the extra crap. So, yeah, we're using Newton's series, which is quite efficient. It's basically we're just summing the 1 over factorial from 0 to infinity. 0 factorial is 1, so 1 over 1 is 1. 1 factorial is 1, so 1 over 1 is 1. Right? 2 factorial is 2, so 1 over 2 is a half. Right? So very quickly in 3 terms, you're already at 2.5. And Euler's constant is 2.71828, etc. Right? So you can see very quickly that this is going to converge. And it actually it actually produces more than 1 digit per iteration, which is beautiful. But there were some things that came up here. So if I do, you can notice this is massively simpler than than the formula for the other one. It's very similar in form because there's a division, so there's a numerator, but the numerator is just 1, and I don't even need this, do I? I don't even need parentheses around the n. That doesn't need to be there. Yeah, so there's one of those little details where I just dropped things in and it worked, but I could have cleaned it up slightly more. I'm sure there's probably a few others. So fiddling around with it, I found that it makes about a little over 1.5 digits per iteration. So if you have like 100 iterations, it'll give you 155 digits of E that are correct. And that next one actually stands a good chance of being either correct or really, really, really close. So I was actually really surprised. I didn't assume that it was going to be the same ratio as the other one. So I just like blanked this out and just made it. I just set the precision to K itself, and every digit was correct when it was coming out, and I was kind of surprised. I wasn't expecting that. So I scaled it. So I just scaled it up to two of this, and it was still most of that. I'm like, holy shit. Okay, this is really efficient. But some things that you might notice if I run this, the runtime is really close to the runtime for the other one. So recall for 100 iterations with the fundamental circle constant, it was taking 0.002, I think. So just slightly slower than this. And if I do 1,000, let's run that. It was taking 0.088, I think. And actually, if I change this to just, well, let's make it a fair fight, right? There. So it's a little bit faster, but it's not massively faster, even though it's doing significantly less. You would think it should be maybe like twice as fast. It's nowhere near twice as fast. So I'm going to replace this. And one thing that you will be able to see when I scale this up, though, the fact that there's more of it here is actually going to factor in really heavily, right? So 10,000 iterations before took, well, what it was actually doing was 5,000 iterations, to be fair, because it was stepping 2 at a time. So here we're stepping 1 at a time. So we're actually running through it 10,000 times. But regardless, it still did the computation 10,000 times because it was doing 2 steps at once. So yeah, it's basically like the heavy lifting it was doing 10,000 times still. Okay, so here, when we do 10,000 with this, you would think since it's lighter, it should be competitive for time, right? But here, let me run this, and nothing's paused. I'm still here, still talking, right? This is live. Yeah, so I put in the link up at the top there. I'll put it in the comments so you can download it. I mean, this is a real short program. You can just write it. It does require MP math for the arbitrary precision. It took me a little while on Linux to figure out how to. Well, it's like, I think this is Ubuntu underneath the hood. I don't even remember. I have computers with all different versions of Linux anymore. So I don't even know what the hell I'm running. But yeah, it took me a minute to figure out how to get that installed correctly, but it does need that. And this, it only needs this to give you the time for that counter there. So this part is not actually required. It's just kind of nice to see how long it takes to do the computation. But really the meat of it is right here. And if you take out all those MPF things, you don't need the MP math, and it'll give you something like 15 digits real easily. So here you're going to need maybe 10 iterations, and we're finally complete. Look at how long that took. 81 seconds, basically. But look at all that. Look at all that. That is still pretty quick. Also, this is a very old laptop computer, so, and this is not using multiprocessing. We're using one core. It's not optimized in that regard at all. So you could definitely get, you probably will, anybody who's watching this will probably get better results than this, better times than this on your machine, because I use a very old laptop that's a laptop, and this code is just using one core. So yeah, whatever. But it's the same machine that I used for the fundamental circle constant. So for consistency, you can these numbers compare directly. So yeah, this took a little over twice as long. Because twice would be like 68, 70 seconds, somewhere in that ballpark. Notice, this is a little bit more than twice. I think that's what it is. I think it's the length is actually accounting for most of it. Which probably means, and the fact that it gets bogged down even at 1,000 iterations, so it's getting bogged down in the same way, at the same scale. I'm pretty sure that means that what we're doing is we are hitting limits with the physical memory management. So you've got slower memory storage devices that it's just slower to access, slower to read and write. And because we're getting big enough, we're having to push into those, and that's really what's slowing it down. So I don't think this is even. It's not even a CPU problem anymore, I don't think. Maybe it is. I don't know. It depends on exactly what's all going on under the hood. And I don't really care enough to figure that out. But it is interesting, because we're dealing here with only basically a couple numbers here. We're doing very little with it, and it's still taking a similar amount of time. So I really don't think it's CPU load. I think it's the memory devices. But let's look here. So this is, well, down here it tells me which column I'm in. That's useful. So how about this 3, this 1173? We're right around 600. Look at that, 1173. It's right there. So this was accurate out to that point. It might actually be accurate a little bit further than that, but pretty much the way that I have this scaled, you're getting, let's see, what is it? This is 1,000. What the hell? What happened here? I don't understand what happened here. Okay. This is 1,000 iterations, but Oh! Yeah, okay, I got you. This is when I was fiddling with that. Okay. I'm like, why is it like... what happened here? It's because, yeah, I forgot what I did. Okay, so here, this one. This 5682. That's at 1500. 5681. So that last digit that it gave us here, that digit is wrong, but barely. So yeah, this truncation is pretty good. It's pretty good. At 100, it's perfect because that's actually what I tailored it to. I did 100 and I found that it was good out to 155 digits. So at 100 iterations, it's exactly perfect. So that 5956, we should be able to see that right there, 5956. So that's perfect up to that point. And then next digit, it was actually like a 29, so it was almost there. And honestly, if you had gone one more and it would have rounded, it would be a 3. And since the next digit is 0, like that 3 would be really, really accurate. But, you know, whatever. I opted not to do that. Yeah, this is nice. This is nice. That's a shit ton of digits. So that's 15,500 digits of E, and I would say maybe somewhere in here, somewhere in there is probably where it cuts off. Here, why don't we just see? Let's go slightly further. Let's just run this, and it'll take another about minute and a half to get that, because I only added a couple iterations. It shouldn't really increase this time too much. We'll probably be at like maybe 81.5 seconds or something like that. We'll actually be able to see, I think, fairly faithfully how long at this point an iteration really takes. So we're at like 80.9 and a quarter, 80.93, something like that. I don't think I have anything more to say about this. Yeah, I hadn't really made any optimizations yet, other than like what I could instantly see in my head. So like the nice thing here with the n factorial, as we step through this, I just have, you know, I named it the same thing, n, and as we step through, I just multiply it by our current index. So that gives it to you, so we don't have to keep computing a factorial every single time. Sort of like with the fundamental circle constant, I optimized it almost exactly the same way, so that you don't have to keep computing powers over and over and over. It did occur to me though, hey, oh, that was actually faster. Okay, so that told us nothing about what was our last digit over here? 77326, 77326. I guess it was. That 9 though, it should round to a 7, so still like that last digit, don't trust it fully, but that's pretty fucking amazing. Holy shit. Alright, so that's at 15,501. This should be at 15,501. Yeah. Okay. So that's, even at 10,000 iterations, it's pretty much bang on. Wow. Okay. That's nice. That's nice. Simple little program, very easy. You could definitely make this faster, but Jesus Christ, why do you need to? Because even at 80 seconds, producing this much of E, what are you going to ever do with this? Look at this. Look at this. What are you ever going to be able to do with that? I can't even copy and paste that. It's so big, I don't think it's going to let me copy this. Let's open an instance of Kate. Yeah, it won't let me paste that. It's too big. It's too big. Oi. So there you go. There you go. Yeah, that's more powerful than you're ever going to need it to be. And it's really just this. That's just the core of it right there. And half of that is comments. Like, honestly, if you take out the comments, there's very little really happening here. The mechanism is very, very simple. Enjoy.